start. So our next speaker will be Rob Gover from the University of Auckland, who will speak about conformal Yang-Mills renormalisation and higher Yang-Mills energies.
Thank you, Katrina. And an opportunity to thank the organisers, especially of the program, of which Katrina is one, and of the conference. It's really great to be here in Cambridge and, as Claude says, amongst old and new friends, so very good. So this is, just to say, collaborative work. So this is collaboration with Emma Latini, Andrew Waldron, Yongbing Zhang. I haven't personally met directly Yongbing Zhang yet, so it's a collaboration on this project that started on Zoom, which was following talking about the sort of first part, which I'll talk about, which is collaboration with Larry Pearson and Caleb Slay, so from quite a long time ago. And it's actually, the first bit I'll talk about is something that is very, very old really, even though it's appeared this year. So there was a final part of it that took a long time to get settled, a sort of example. Okay, so, and just to say, it's been great hearing all these very, very well-developed topics, and you know, a bit intimidating to see how much fantastic work's been done. This is more the start of something, and there is a connection to Twistors, but only only a sort of light connection through use of the tractor connection and so on. So I'll mention that when it comes up. Okay, so just to get things going, so what I want to talk about is some invariants and equations that you can make with connections. So what do we mean? Well, you know, one of the ways of talking about a connection, you would start with a principal bundle, so a principal G bundle for some Lie group G. And in the context that I'll be talking about it, people would often ask that be compact. I will want it to be compact or have similar properties when I need it, and then I'll drop that and I'll be using it in cases where it's not the case. So just watch out for that. But anyway, it's fine. Then if you have a finite dimensional G module, then you get associated vector bundles. And if you have a connection on the principal bundle, it's going to give you connections on the associated bundles. Which is all to say that really what I'm going to be, and I'm going to really fix in any case, this V or this bundle that you get, this bundle. So really we're just looking at linear connections on vector bundles. And then I'm going to write F for the curvature, and you know, I'll mention the connection sometimes, or I'll drop it from the notation when it's obvious. And then just to recall that when you have a connection on a linear connection on a vector bundle, no matter what, you have this differential Bianchi identity, because this just follows from the Jacobi identity. So that's always an exercise I give students. Now, what we want to talk about is suppose you have a Riemannian structure, so say Mg, M will have dimension n. Most of the things I'm talking about won't matter what the signature is, but just to keep life simple and not to have to make sort of cautious statements every now and then, I'll just assume it has Riemannian signature. But really what we want to do is move to a conformal structure, so everyone knows, so if you have a metric and you have another metric which is a positive function times the metric you started with, then we say they're conformally related, and this is an equivalence relation. And then the equivalence class of those things gives you a conformal structure. So if you're starting with a manifold that just has a conformal structure, that's often the situation I want to talk about. How do you sort of couple this conformal geometry to connections like this to create sensible conformally invariant objects that are also, you know, gauge invariant, so they're invariant overall? That's a sort of basic problem to think about. Now, of course, everyone in this audience, much better than me mainly, knows well a very special case of this, where you use this all the time, and that's with the Yang-Mills setup, right? So, just to remind those who are perhaps not familiar, in dimension 4 I'm talking about, So this starts with the Yang-Mills Lagrangian density. So I'm writing down in a complicated way up there. This L is what you might otherwise put as minus F squared. So in other words, I'm contracting off the indices using the metric or a metric from the conformal class if we're in conformal. And then, but then the curvature takes values in endomorphisms of the vector bundle. You're composing and then tracing, right? And then, that's a negative quantity. So that's why I put that minus there. Now, the key observation, which, goes back a long time, presumably to Yang and Mills, is that under a conformal rescaling, how does this thing change? Well, the only way the metric's entering here is rather trivially, it's just contracting away these indices. So that the Lagrangian density just transforms. If we change the metric to e to the 2 omega g, where omega is a smooth function, then this Lagrangian density transforms by e to the minus 4 omega because of these inverse metrics used here. Okay, but on the other hand, if you look at the measure induced by a metric, how does it change conformally? When you change the metric conformally in the same way, well, it's with a plus 4 omega. So the product of the Lagrangian density with the measure is then pointwise invariant, if you like. And so this integral is conformally invariant. And I don't need the manifold to be closed to say that. But if we want to do variations, and it's simpler to think about it that way. So you get a conformally invariant integral starting with your connection. Because that's conformally invariant, it follows, of course, that if you take variations of connection, that sort of doesn't change the conformal structure, the metric at all, then that will be conformally invariant. So the functional gradient of this with respect to variations of the connection has to be conformally invariant. The functional gradient is the left-hand side here of the Euler-Lagrange equations. So this delta is the formal adjoint of this twisted exterior derivative that I wrote down. Okay, so this is just the sort of twisted divergence of the curvature being 0 as the Euler-Lagrange equations. But the point I want to make here is just, first of all, that we've constructed a couple of interesting invariants, albeit in an easy situation here. Namely, we've made this functional gradient of the action. That's a pointwise conformal invariant that links the connection to the underlying conformal geometry. And then, of course, it's the integral itself, the action itself, is a global conformal invariant. So one of the things I'm interested in is can we do things like this in higher dimensions? So this conformal invariant of these Yang-Mills equations, it's true in dimension 4, but the usual Yang-Mills equations are then not conformally invariant in other dimensions. So do they have sort of related equations in other dimensions and things? That's part of the motivation. Whoops. Okay. Because we're talking about conformal geometry and because it's me, I'm going to introduce the tractor connection. So the usual mantra that we say here is that in general there's no preferred conformally invariant connection on the tangent bundle of a conformal manifold if the conformal structure is all you have. You may have other structure which induces such a connection, but if you just have a conformal manifold, there isn't. But there is on a small extension of the tangent bundle. So here's my notation for the cotangent bundle, twisted by something which is giving a weight. That something is just the root of the canonical bundle, and here's the sort of what root it is. So you take the top exterior pair of the tangent bundle. That's a line bundle, of course. If you square it, it's then a trivial line bundle, so it's a trivial real line bundle, so you can take roots without thinking, and then you take the 1/2n root of that, and that gives what I'm calling E1. Now we could make, and you'll see it here, there's a -1, that's of course the dual of that, but you can put other weights here, and that would just, so if you put a W weight here, that just corresponds to putting a W over the 2n there. Now, So that's the tangent bundle twisted by that line bundle, and I'm just adding, it's really a direct sum, if you like, of these two line bundles. So E1 and its inverse, I've got the semi-direct sum up there because as an invariant object, these things mix up a bit. And this bundle, for instance, is a sub-bundle of the whole thing. This bundle is a quotient of the tractor bundle and so on. So by the way, this is also one of the connections to twistor theory, because in dimension 4, many of you will be familiar with a connection on the local twistor bundle. And then if you take so wedge 2 of the local twistor bundle, then that's what this tractor bundle is in dimension 4. And that's in a sense, from our point of view, I mean, the tractor bundle is due to Tracy Thomas, who was a contemporary of Cartan. But from our point of view, we were using the local twistor idea of building something very explicit and simple that captured the Cartan connection, and it was influenced a lot also by the ambient metric construction of Pfeffman and Graham, which I'll touch on later, but not in relation to the tractor bundle. Okay, so, but the main point for us is that now you have a bundle that does have a conformally invariant connection. So and it's very simply related to the Levi-Civita connection. Here are the 3 sigma, mu, and rho are related to these 3 slots up here. And then this is the Levi-Civita connection appearing first in all these things. P is the Scouten tensor, which is just a trace modification of the Ricci tensor. So if you just sort of wearing your beer goggles, it's almost the same as the Ricci tensor. So here's a simple explicit formula. This connection also preserves a metric on the bundle, so a bundle metric. And I'm giving it here as a quadratic form. So if sigma mu rho is the triple again, here it is 2 sigma rho plus mu. And so you'll see from that quadratic form that if you're in Riemannian signature, that this bundle metric then has Lorentzian signature. Okay, so it always has some signature. Anyway, so then you can build up a whole calculus around this, and in particular, it gives you a sort of simple practical way to conformal geometry, because historically, I guess a lot of what people were doing, apart from, there were enlightened people like Cartan and Thomas and so on, but a lot of the work done in conformal geometry to find invariance started off by writing something down involving the Levi-Civita connection, so for some metric G, and when you wanted to write it for the metric G, the related, conformally related metric, you got the old thing that you had plus a big mess, and the aim of the game was to play around and get rid of the mess. But of course, if you can start with an invariant connection and just work all the time with invariant things, then you avoid making this mess in the first place. So that's the sort of way we want to think about it. And a simple example is you have this connection, so you have its curvature. That's then conformally invariant. What is it? Well, that's the length squared of the Weil curvature. So the Weil curvature, remember, is the completely trace-free part of the Riemann tensor, which is well known to be conformally invariant. Now, yep.
Is symmetric? P.
Pardon? P is symmetric, yeah. It's really a trace modification of Ricci. So if you're in dimension n, Ricci is n minus 2 of P plus G of J, where J is the trace of P. So that's it's just that.
I would have guessed it'd be a contribution from the norm of the Couton tensor. In addition to the Weil tensor.
The which tensor? The Cotton, you mean?
Couton. Yeah, his name is
yeah.
Couton.
Oh, yeah.
It looks like cotton, but it's Couton.
Yeah, no, but that's because it's parabolic. That's in the degeneracy. So it doesn't contribute to that. Yeah. So it was a good guess, but not correct in that case. Unusual for you, Claude. Right. Okay, so we mentioned Yang-Mills, we mentioned a tractor connection, that's a conformally invariant connection. So you go, what if we use the Yang-Mills equations on the tractor connection itself, right? Why not? So we can ask what the Yang-Mills invariance. We had this action and we had these Yang-Mills equations, and this is something obvious to play around with. And in fact, you get some old favorites, as I say. So suppose you take the tractor curvature, so you'd make this tractor Yang-Mills action, if you like. But as we just commented, the sort of the length squared of the tractor curvature just picks up the Weil curvature. So you get this, this action that turned up a long time ago in general relativity for an attempt at conformal general relativity due to Bach. So this is often called the Bach action, which is the integral of Weil squared. So we're in dimension 4 here, I should say. Okay, so that's a sort of old favorite. And then there's this theorem, and by the end of this lecture, I'll be able to add more names here, no doubt, because every time I mention this, someone says, aha, it wasn't first due to those people, it was first due to someone else. But anyway, what it's saying is if you take the four-dimensional tractor Yang-Mills equation, so we're just, you put delta F equals 0, but now you're using the tractor curvature, what do you get? Well, you get a lot of zeros, so this is a tractor, it has a lot of slots. And then the only little pot of gold that's not 0 is the Bach tensor, right? So the Yang-Mills equations for the tractor connection, or you could think of it as the local twistor connection, more or less, is the Bach equations on the nose. Now you might go, well, if you know about this Bach conformal gravity, you might go, well, that's obvious because how was the Bach tensor invented? Well, it was invented as the functional gradient of the integral of Weil squared. So you might go, well, you're doing variations, so of course Bach's going to turn up. Well, it's going to turn up, but all of these zeros in it being exactly Bach is not completely trivial, because remember, these Yang-Mills equations have come from taking a variation with respect to the connection and not with respect to the metric variations. Okay. So it's, because dimensions are low enough, it's perhaps not too surprising, but it's very nice. And this gives you a handle on the Bach equations via Yang-Mills type equations, which can be useful because the Bach equations, and I'll come to this later, are a sort of weakening of the Einstein condition. Okay, now what we really want to think about is, is there a higher dimensional analog of this picture? So some of the things I'm saying, they're sort of features that look interesting, and they give us a bit of a motivational structure in our search for this question. So that's what I'd say. So is it a four-dimensional story only? Are the Yang-Mills equations that conformally invariant in dimension 4? Is that the end of the line for connections in conformal geometry, or does it go on? So that's a sort of main question. And then we can say, well, there's this thing called the Bach tensor. Is there a higher dimensional analog of that? And then are these things related? The questions might be related given the motivation I've given, right? So that's the way I'm thinking about it. Okay, so on the intrinsic geometry side, then there is a higher order analog. So the Bach tensor is the dimension 4 case of a chain of conformally invariant objects that we now call the Pfefferman-Graham obstruction tensor in each dimension. So in
the power, it would help if you put it in some parentheses, because it looks like n over 0, but it's quantity n over 2 minus the integer 2. Right?
Oh, sorry. Okay. Yeah. Well, you're wearing different beer goggles to mine.
Yeah, that's right.
To me, it looks just so. That's an n over 2 minus 2. So in particular, it is, n over 2 minus 2 is 0 in dimension 4, and then that's the leading term of the Bach tensor, which would then have Weil contracted into Scouten as the next term, right? But in higher even dimensions, there's in dimension 6 you'll get one Laplacian here. On this double divergence as leading term in dimension 8, you'll get a second Laplacian power, and so on. So there are conformal invariants like that, going up. These things are not too bad to study in low dimensions, but as you can imagine, this game the mass turning up means that they would be hard to discover by hand or even with software in higher dimensions. But there's a construction due to Pfefferman and Graham that I'll talk about, and this ends up being a certain obstruction to its construction. And it's conformally invariant, so that's how it was discovered. But it recovers in particular the Bach tensor and then generalizes it to higher even dimensions. Okay, so another feature that I particularly want to emphasize here, and you'll see why shortly, is that another way of seeing how this Bach tensor arises, it's the functional gradient with respect to metric variations now of the integral of the Q curvature, or sometimes called the total Q curvature. So what's the Q curvature? Well, I'm not going to talk a lot about the Q curvature, but it's due to Branson and Ørsted. First appeared in Dimension 4 in a paper of Tom Branson with Bent Ørsted, but then Tom Branson generalized it to sort of all even dimensions. And I think there were other people buzzing around that idea at the same time. But basically, so it's a scalar conformally invariant, but it's relatively high order. One of the important things about it is that under conformal transformations, it transforms like that, okay? So if there were just this first term, it would be conformally, well, covariant or invariant. And notice that this, so this is when we're doing this change of metric from G to G hat, so e to the 2 omega G, I guess I'm doing here. And so this is exactly the conformal factor that means that you would be able to integrate it were it not for this other term here. But in fact, you can integrate it on closed manifolds because this other term is a divergence. So what this is this is the critical GJMS operator. So there's another link to Twistors here, and I should have highlighted in blue the M there because that's Mason. So it's Graham, Jen, Mason, and Sparling constructed this family of operators. So the first operator, GJMS operator, is the familiar Yamabe operator or conformal Laplacian. And that's just, one Laplacian plus a bit of scalar curvature. And then there's one where there's a Laplacian squared plus some lower order terms that's usually called the Panet's operator. But a bit like I was saying with the theorem on the previous page, or the result on the previous page, that at various talks and things, people have pointed out that it was known before Panet's, so it was actually known in the physics community before Panet's constructed it. And it was independently constructed by many others, including Mike Singer and Mike Heston. Mike Singer's here. so yeah. Anyway, so there's a whole chain of these, and they're very well known. And so this Q curvature transforms like that. And so if you know about how the Gauss curvature transforms in dimension 2, it's exactly in this form, but where you'd have a 2. So it's in a sense like a higher order generalization of Gauss, and if you're thinking of curvature prescription problems and such things. Okay, but anyway, so this says that there is a higher order generalization of Bach. So what about the corresponding Yang-Mills side? Let's go back to that. Okay, so some stuff here. So it turns out these GJMS operators, which generalized, if you like, the Yamabe operator to higher orders, or are part of an even bigger picture if you allow differential forms. So here I'm writing these curly EKs, that's K forms, so E1 would be 1 forms, E2, 2 forms, and so on. So there are conformally invariant differential operators between K forms. So I'm taking here K between 0 and n over 2. Let's say we'll be careful with, well, I'm not being careful with the parity here, but I'm really thinking of even dimensions. So I should have actually said that. So we're on an even dimensional manifold, so n is divisible by 2. So then there's conformally invariant operators, actually, anyway, think of it n as even, but it can be odd for part of the story. So they're of order 2m, that's what the m means. They go between K forms and K forms. They have weights, I told you what weights were, and the leading coefficient is actually determined by the weights like that. Delta, remember, is the formal adjoint of the exterior derivative, and these exterior derivatives are sort of, you can think of everything as kind of Levi-Civita connections, but acting in a skew on skew forms and so on. Okay, so there's there are these differential operators between differential forms that in a sense are like Laplacian operators. So they generalize the GJMS operators. But something very nice happens in what we call the critical case. So remember there's this notion of the critical GJMS operator. That's the one that's of the order of the dimension. But for these, the key thing is that the weight is 0. So in this family, when the weight is 0, this part of the leading term drops out. And in fact, what I showed with Tom Branson quite a long time ago is that in the critical case, these operators take a very special form. They're formally self-adjoint, and they're delta QD, where Q is, perhaps whatever you need to put in the middle here, but the operator factors through, it's acting on forms of weight 0, so it factors through the exterior derivative, and it's formal adjoint in that way. But the middle bit is not something that you should ignore as just something. The middle bit is exactly a type of Q operator, so it generalizes the Q curvature to something that can deal with forms. So it's not just a scalar now, but it's actually a differential operator. And it's not conformally invariant, but it's nearly conformally invariant. And in particular, it transforms exactly like the Q curvature, provided you act on closed forms. And there's a family of these objects, and the usual Q curvature is one of these things, but acting on 1, which is a closed 0 form, of course. So the interesting thing is that, sandwich, you can then build these operators out of these Q operators. And then another feature of these Q things is that you can use them then to pair closed forms. So if you act on a closed form with Q and then contract in a closed form from the other side, you get something of exactly the right weight to integrate, and then so this gives you a pairing on closed forms. So in dimension 6, to illustrate, to give you a sort of picture to go with that, so here's the de Rham complex. 0 forms, 1 forms, 2 forms, exterior derivative, 3 forms. Here's 4 forms, but written as 2 forms with a weight. Here's 5 forms as written as 1 forms with a weight using, say, the Hodge star, and so on. Then there are some long operators. Coming from 2 forms to 3 forms, you can go in with the exterior derivative, of course, but then you can go in and Hodge star. So there's 2 things you can do coming in here. There's 2 things you can do going out. You can do the exterior derivative, or you can Hodge star and then do the exterior derivative. So surviving that is a composition that's not 0, which you might call the Dirac operator, delta D. So it's now acting on 2 forms. And then on 1 forms, you have this long operator, we call it, which is delta Q2D, where it's Q2 from up there. And it's this Q2 we'll really focus on. And the longest arrow in the picture is this critical GJMS operator. So that shows how these things fit together. Bless you. So looking at this Q2 operator, how does it look explicitly? So this is second order. We're going to fix dimension 6 now. So it looks like this. So here's a closed form. So it's d delta on U plus the Panizzi operator acting algebraically plus the trace of the Panizzi. Okay, so, sorry, Panizzi. I said Panizzi, I meant Skelton. Right, so d delta plus Skelton acting algebraically plus the trace of Skelton. Okay, now, because of its low order, something nice happens. This Q can be actually coupled to connections. So when you have a conformally invariant object or an object that's nearly conformally invariant or something, usually if you couple it with a connection, that will cause a lot of damage. So if it's conformally invariant, it won't generally remain conformally invariant. For the first order, of course, things do, and for second order, they do if you're careful or lucky, right? So in this case, if you couple this to a connection, it actually retains its properties exactly. So in other words, if I couple with a connection and act on a two form that takes values in some bundle on which there's a connection A, but this thing is closed in the twisted sense, then this Q still transforms exactly like the Q curvature, the Q operator did. Okay, so you just need this strange property that it's DA closed, and you might think that that's, well, just a curiosity because, you know, you have to then go around looking for DA closed things. On the other hand, I wrote one down right at the start of the lecture, namely the curvature satisfies Bianchi, so it's DA closed. So in particular, we can apply this to the curvature of a connection, and then when we couple it again with the curvature to form a scalar quantity, then you get something that transforms exactly like a Q curvature. So so in dimension 6, it's a type of Q curvature that you can associate with connections. Okay, so here, you know, almost all constants are treated as 1 at the start of this talk. So, but anyway, so the way this then transforms is e to the minus 6 omega. So this is under the g going to g hat is e to the 2 omega, and then plus a term that factors through d and is a divergence term. So that drops out when you integrate, and that's the right weight to integrate over 6 manifolds. And so you can form this action again, which is conformally invariant and by construction gauge invariant. Good, so then you can take the variation, of course. So, so this is now a candidate for a higher Yang-Mills energy in dimension 6. And its functional gradient with respect to connections, you can just compute. I've written it here in a sort of brief form. So it's delta, this Q2 operator acting on F, plus a bracket term and so on. And it has the leading order of delta D delta like that acting on the curvature. So we know that's the right leading order because of conformal invariance, and you know if you go to the abelian case, if you like, this would be just a 2 form, and then you have the sort of usual classification of invariant operators in the conformally flat case. So you know how the thing had to look at the start, and it's exactly right. So it has the right leading order terms. So you know that. So we sort of we say this is the higher Yang-Mills system for dimension 6. So to put this equals 0. So it really is a nice analog of the Yang-Mills equations, but higher order and for dimension 6. Now, you know, as a test, and this is what took the years to get done. so the sort of main bit of this was done a long time ago. It's too embarrassing to explain, but we were sort of trying to get this calculation done, and yeah, it took a little while to get done. So, but anyway, so the upshot is, you know, this is a small theorem, but it took a little while for us to write it down. So is that when you pop the tractor connection into this thing, so you ask the same question. So now you're in dimension 6, and you feed the tractive connection to these Yang-Mills equations. And what it pops out is exactly the Pfefferman-Graham tensor, again with zeros, right? So, so there's a lot of information in the zeros. So the Yang-Mills equations on the tractor connection in dimension 6, or these higher Yang-Mills equations, boil it down to exactly the Pfefferman-Graham flat condition. Now here's a sort of application in inverted commas. It's more like directions for an application. So what I want to say is this Pfefferman-Graham tensor is a weakening of the Einstein equations, and the reason is that Pfefferman-Graham have this construction that's called the Pfefferman-Graham ambient metric. So if you start with a conformal manifold, it's meant to be a conformal structure, then what they do is build a bundle of rank 2 greater than that, which first of all you have the ray bundle of metrics in the conformal class over your conformal manifold, and then they add on one more dimension. Just take the cross product with Cartesian product with the reals, for instance, and then on here they construct or attempt to construct a Ricci flat metric that's canonically associated with this structure. And so there's lots of things that pull back to this line bundle. So you're trying to match that up and solve a Ricci flat problem here. So that's the Fefferman-Graham ambient metric. Now, in particular, they attempt this formally, and this Fefferman-Graham obstruction tensor that I mentioned is the obstruction when the manifold you started with was even dimensional, then this is obstructed for smoothly obstructed at finite order, and that's the way this Fefferman-Graham obstruction tensor turns up. But now the point is that if your original manifold was conformally Einstein, in fact you can do just a sort of warp product type construction and make the ambient metric completely explicitly to all orders, right? You just construct it. So it must be that when it's conformally Einstein, there is no obstruction, and so that shows you that this obstruction tensor vanishes when you're Einstein. Okay, so of course it was well known earlier that the Bach tensor vanishes on Einstein manifolds, but that comes out as well because the Fefferman-Graham obstruction is the Bach tensor when you start with a 4 manifold. But in dimension 6, these high Yang-Mills equations are equivalent to the Bach, which is then a weakening of Einstein. So that's really all I wanted to say. So it gives you more handles on attacking Einstein from the conformal point of view. Okay, so that's sort of the end of part 1. So the point is this trick that we use to do that in dimension 6. At the moment, parts of it really don't work when you go to higher dimensions, so you need other ideas. So they might work with adaptation, but they don't work as stated. So now I want to talk about something that at first looks completely different, so namely Poincare-Einstein manifolds. So here, first of all, let me mention a conformal compactification. So I've also drawn the picture over there so I can point at it later. So I want to start with a complete, let's say Riemannian metric. And what does it mean to be conformally compactified? Well, that means you've found a manifold with boundary, M bar, so you can also see on the board over there, that's the whole thing with boundary. So that's now a compact manifold with boundary, such that the original manifold is the interior, okay? And on the manifold with boundary, you have a metric that goes to the boundary. So it's a metric on the whole manifold with boundary. But it has the property that on the interior, it's conformally related to this fixed geometric or physical metric that you started with, G+, and it's conformally related in a special way. So G+, the original complete metric, is sigma to the minus 2g, where sigma is a defining function for the boundary. So the boundary is the zero locus of sigma, and the derivative of sigma is nowhere zero along the boundary. That's what it means, right? Now, the point is that given any such defining function for the boundary, then you get a g determined by G+, and the g determines a metric on the boundary. But you could change your mind about this defining function, so you could multiply it by a positive function, that's the freedom, and then that will just conformally rescale this metric g, and so conformally rescale the metric that's induced on the boundary. So what you get canonically from M and G+ is a conformal structure on the boundary, and this conformal compactification is then a machine which can link the conformal geometry on the boundary to this Riemannian geometry on the interior that has that as its infinity. Now, the conformal compactification is called Poincare-Einstein if the metric G+ is Einstein, and that's the case I want to restrict to mainly. And just as a point of notation, now the boundary is going to have dimension n, and the interior is going to have dimension n plus 1, which I'll call d. Okay, so now what we would like is to solve some Yang-Mills thing. Well, not really solve it, but talk about solving it. Look at the formal aspects. So looking at the picture here, we want to start with a connection on the boundary and then find a connection on the interior, on the bulk, as we call it, which is compatible with the connection on the boundary, so it has that as its boundary value. But this one solves, in a sense, the Yang-Mills system on the interior. So that's the problem, and we want to, at least in this talk, just look about the formal aspects of this, so solving that formally. Okay, now, initially there's a problem, right, because here's the Yang-Mills equations. Nabla here is really this coupled connection of the Levi-Civita for the interior with your connection that you're trying to solve the Yang-Mills equations for. But of course, G plus is singular along the boundary, so over there, G plus is singular, and so the Levi-Civita connection is not defined in the boundary. Nevertheless, nice things happen. So, in fact, this left-hand side can be written as the defining function times a vector field, or one-form field, if you like, taking values and endomorphisms of the vector bundle that we have connections on. We call this the Yang-Mills current, but actually this does extend to the boundary. So what happens is this actually becomes 0 at the boundary, and the way it becomes 0 is sigma times this current, and this current is given by sigma times the divergence of the curvature, but now in a metric that goes to the boundary, so that this bit makes sense now, and then this normal hooked into f, where n is the derivative of this defining function. Okay, it's really a weight 1 density in the way we do it, but that's a detail. Okay, so this is then actually conformally invariant. If that's a weight 1 density, this is really conformally invariant. So this extends it in a nice way to the boundary, and it turns out that's the right way to do it. Okay, so the problem is, given a connection along the boundary, as I said, you have a connection along there, find a smooth connection on the bulk such that its boundary value is the connection that you started with, and then that this current vanishes to as high order possible, right? So then we'll just try and solve that formally. Okay, so that's what we want to do. Now, okay, so you set that up, and then the first thing is, well, you can actually do this. You can just solve this formally, order by order, up to some order, right? So how does that work? So here's the proof idea. Okay, this is working out what the clocks meant. Okay, so here's the proof idea. So here's this current, and suppose you've solved it up to some order L, time, and K is what you're left with there. So you've got it like that. Then actually, if d minus 1 is not equal to L, then you can show that this normal into K is 0 along the boundary. So this K is sort of tangential to the boundary in that sense. Everything here is taking values and endomorphisms of this bundle that the connection's acting on, and that's sort of suppressed in the notation. Now, actually, and I'm going to say some things here, but secretly in what we're doing, we're also using that this defining function solves a singular Yamabe problem. I mean, it's really coming because there's a parallel tractor. Because it's Poincaré-Einstein, that means that, so Einstein means that there's a thing that we call the scale tractor. Actually, I probably should mention that because it's another link to twistor theory. So Einstein means that there's a certain tractor which is parallel. and this is the thing we call the scale tractor. Anyway, the link to twistor theory is that if you're a twistor person, you might call that the generalized infinity twistor. So it's really very closely related to what was called in twistor theory the infinity twistor. So, but anyway, because that's parallel, then the scale satisfies equations, and in particular, it satisfies a singular Marby equation, which for our purposes, it's giving you a constant scalar curvature condition, which of course you get from Einstein, but a singular version because it works up to where the zero locus is. And then that sort of simplifies a lot of this analysis. Now anyway, we now just recursively solve this Yang-Mills thing, and here, after a lot of nice grooming and using this sort of lemma up here, you see that the way it goes is extremely simple. That if you have the connection that solves this up to order L-1, then you get the J from that, and then you just divide it by these numbers and the length squared of n, and then that gives you the adjustment that you make to the connection to go to the next order. So in the end, after lots of sort of careful work, you can make it look very simple. What one sees in particular about this is that this up to n d minus 4 is sharp, right? Because here you have d minus 3 minus L. So this is going to go wrong when L is d minus 3. Okay, so it's going to go wrong in the sense of solving it, but good things happen, because those of you familiar with these sort of problems will know that at this point something nice happens. Namely that when you can't solve it, it exactly means that this J has a sort of invariance, and that translates onto an invariance of this K. So the abstraction, the bit where you can't go any further, actually gives you then an invariant made out of these things, so out of derivatives of the connection and so on. So you get a conformal invariant because the whole setup is conformally invariant. And so that's what we call the obstruction current, right? So it's the obstruction to smoothly solving this problem. Now, also, if those of you who know about such expansions will go, oh, you can fix things with a log term, and that's right. So another way of understanding this obstruction current is that you put it in as a log term, and then you can keep going. Well, there'll be a term that's formally undetermined at around the same order, but without a log, right? So at the next order, you would have this sort of adjustment. So L is undetermined, this one is determined, that was the obstruction to smooth extension. And then you can keep going, but you have a polyhomogeneous expansion, so you now have these log terms. Okay, but anyway, here's the theorem that that these K's first of all conformally invariant, these things that are the coefficient of the log term or the obstruction, and using some properties of the Poincaré-Einstein expansion in what we call Graham-Lee coordinates. But these Poincaré-Einstein expansions have been done a lot, so we know a lot about how the metric in a Poincaré-Einstein manifold extends off that boundary over there. So if n is odd, then these obstructions vanish completely in the Poincaré-Einstein setting. So there is no obstruction then. You still have an undetermined term that you have to specify. But when it's even, it is obstructed, and what do you get? Well, if the boundary has dimension 4, then the obstruction current is exactly this left-hand side of the usual Yang-Mills equations. It's conformal invariant made out of connections in dimension 4. If you're in dimension 6, you exactly get this thing that was this functional gradient of the integral of that curvature, Q curvature that I made earlier, that action that we constructed in the first part of the talk. So you get the higher Yang-Mills left-hand side as the obstruction in dimension 6, and then, as you might guess, in higher even dimensions, this produces what you would want to call higher Yang-Mills systems in the even dimensions as the obstruction to extending off. Okay. Now, so that is these higher Yang-Mills equations turning up as abstractions to this problem, or as log terms, if you want to do it that way. Are they variational? Yes, they are. And how do you see that? Okay, so let me go back over to this picture. So suppose you wanted to take the usual Yang-Mills energy and integrate it on this Poincaré-Einstein manifold. So, I mean, with respect to the metric G+. Well, of course, this is an infinite volume manifold, and you would expect, and it's true, that that energy will be divergent, right? So it'll be infinite. But what you can do is you can regulate it, and this is, again, a sort of familiar story for lots of people. So you cut the manifold off a little bit. You think of it as a small amount, but I'm drawing it a bit bigger. So it's epsilon, in a suitable sense, away from the boundary. And now the manifold that's left, you call it M epsilon C. So this is the truncated or regulated manifold. So now it's a finite volume manifold, and in particular, when you integrate this Lagrangian density, the usual Yang-Mills one, over the regulated manifold, then of course it's finite. And that's, well, of course that depends on the epsilon you picked. But what you can do then is look at how that depends on epsilon, right? How that integral depends on epsilon. And you get this Laurent type series, so here are the terms that become divergent. You get this Laurent type term with these divergence terms, so as epsilon goes to 0, these all blow up, and as does the log term. And then there's a part that people sometimes call the renormalized object, so that would be the renormalized Yang-Mills energy, and then, and on you go. Now, we're going to focus at the moment on this term, on the archive now, but you won't see it for a day or two as something talking about this term in dimension 6. But so this term, this coefficient of the log term in this expansion is, because it's a log, it doesn't interact as much with these other terms. So it's independent of the terms, the way you did the cutoff, so to the choices that you made and to cut that off at epsilon. Well, with some care, that's true. But even more than that, if your connection A on the bulk, so we now have a connection in here, if that's an asymptotic solution of this Yang-Mills problem that I set up, this formal one, so you solve that formally to the order that you can until you hit the abstraction. That's what I'll call an asymptotic solution. Well, if it is an asymptotic solution, then that's enough for this energy term in that integral, that coefficient of the log term. The integrand is then actually, this term, and you can think of it as getting the integrand, is determined by the boundary data. So it really becomes a pointwise invariant of the boundary data. So we give a holographic formula for that, which involves the trace of f squared and then some operator acting on it d minus 5 times. So, but yeah, the main thing is that this becomes a pointwise invariant of the boundary that you can determine if it's an approximate solution. So what this I dot d here, so this is using this scale tractor contracted into a thing called the Thomas D, and it gives you a nice calculus for working such things out. So this is a very clean formula for it holographically, and then you can unwrap what that means and get actual formulas for these energies explicitly. So here in low dimensions shows what it is. What is it if n equals 4? That's the boundary dimension now, so the bulk has dimension 5. Then this energy term is the usual Yang-Mills energy, right? Because that's conformally invariant, you're integrating it over the boundary, that's not surprising. Then in dimension 6, for example, what is this energy in this log term in the energy expansion? Well, so it's the integral of this thing, which was this Q that we came up with in the first part of the talk, plus some terms that on a closed manifold would integrate to 0. So it's should be bars on that. So everything's here in the boundary. The bars mean the boundary structure, and so these are some divergence terms that you can add to that, and this is the point. This is actually now pointwise conformal invariant made out of connections. So this wasn't conformally invariant, but these transform in a way that fixes the failure of that to be conformally invariant. Okay, and then finally in this this sort of part of the story, these the functional gradient. So this works in all even dimensions. I've just written it down for 4 and 6 to link it to the other parts. But the functional gradient of this energy that we gave the holographic formula for is a non-zero multiple of the obstruction current. So these energies give you a primitive for those what I said would give you higher Yang-Mills equations. And the way you see this, of course, to do it in all dimensions at once, is you go back to that expansion. You go back to the expansion of the. That's it there. So you go back to this expansion, and you look. You're doing variations of this thing, but you do it along. Approximate solutions of those Yang-Mills equations. So you do your variation on the boundary, and then compute what that does to this, and then you look for the log term in there, and that's how you see. So that's what I'm saying down here. That's how you get this result that the functional gradient of that term gives you the obstruction current. So these energies that you get this way give you high Yang-Mills energies. Sort of in all even dimensions, and they're 0 in the when the boundary has odd dimensions. Okay, so finally, just to say a quick comment about the Dirichlet-Neumann type map. So coming back to this diagram, so you're starting from boundary data. The Dirichlet data is a connection on the boundary. So you can imagine solving this problem so that we're not doing that, but we find some tough people who can maybe, and so you solve this problem globally. Now we looked at the formal aspects, and in the formal aspects there was a term L that I said was formally undetermined, but that term is exactly the global information. So if you have solved this globally, then so this L term captures the sort of global information. So the map. When you take a connection along the boundary and then you map it to this thing here, this is a type of Dirichlet Neumann map, or scattering type map. So so that's what I'm writing here. And then what we sort of also can construct in this paper are the conformally invariant operators that extract that term L if the obstruction's 0. Well, sorry. And this is now in the case when the boundary is odd dimensional, so the obstruction vanishes, and then we can write down these explicitly conformally invariant differential operators, so that when you apply them to the ambient curvature along the boundary, they extract this Neumann type data, which is the global term if you've solved the problem. Okay, well that's I think all I wanted to say. Let me check. Yes, good.
Any questions?
Lionel? Yeah.
Sorry, just a comment really that these 6-dimensional theories came out really very naturally in some ambidextrous room constructions that David and I came out with a few years back. So there's this double copy.
The stuff on what?
There's a so-called double copy story that relates Yang-Mills amplitudes to gravity amplitudes. In 6 dimensions, there was a story developed by Henrik Johansson, which took your conformally invariant Yang-Mills and double copied it to a conformally invariant gravity, which these amplitudes are also constructed by us using polymorphic maps to the 6 quadrant of the twistor space for these things. So there's a lot of intriguing links there, but it sort of stops there. So this story that those conformally invariant theories have analogues in higher dimensions, which are no longer conformally invariant, and that's what these ambitwistor strings give in higher dimensions.
I see.
In these boson plots.
That's good. So there's even more links to twistors. So that's good.
Yeah,
anyway,
yeah,
I should get those references off you for that. Yeah, thank you.
Useful to see them coming out.
Any other question?
Apologies if this is something you've already sort of answered and I just didn't quite extract it. But so in 40, there's this story that if you take the Bach action and you impose Neumann boundary conditions on it, it's equal to the renormalized Einstein-Hilbert action up to some constants. And this is a useful statement because it can be easier to compute certain things in conformal gravity than it is in Einstein gravity. This way you can bootstrap answers in the theory you really care about. Do you know for these higher theories, if you make some kind of 2-derivative truncation on the boundary, and then you take your action for the tractor connection, do you get the Einstein-Hilbert action up to some proportionality constant? Is this something you can see?
I haven't thought about that in detail. I suspect things like that happen. In fact, there's some other tools that have come out recently by Jeffrey Case and others that probably suggest in a different way that things like that work. But I haven't thought about it in this context. Yeah, Stephen?
In the 4-dimensional renormalized volume case, there's the Gauss-Bonnet formula. Is there any kind of index type?
No, not as far as we know. No, so that's right. This Q, for instance, thing that turns up doesn't seem to be linked to something like that. I mean, there's no sort of obvious candidate because it's an even invariant, so it's not churny in that nature. But it can't give you the Pfaffian or anything, of course. So but there are tricks that you can do that avoid having to do that. Yeah, Claude, you.
Yeah, so in 4 dimensions, there are large, interesting known classes of metrics that are Bach flat but not conformally Einstein, in particular the half-flat metrics. Mm-hmm. When you look at this generalization of Bach to 6 dimensions, are there any known classes of metrics that are not conformally Einstein but nonetheless are Bach flat?
Fefman grand flat. I don't know, but I suspect there will be, but there's nothing like half flat. I mean, that people have thought about trying to get sort of instantony things in higher dimensions, but as far as I know, that hasn't led to solutions to this in this case. So yeah, I don't know, but I'm sure there'll be obstruction flat things that are not Einstein. Depends on how restricted. So on closed Riemannian manifolds, it might not work out, but I still think there would be, but I don't know for sure. But certainly in more general situations, of course, there would be. Yeah.
So on compact manifolds, it's very hard to find other than in 4 dimensions, other than the half conformally flat conformally Einstein. It's very hard to find. There are no known on compact manifolds, but actually, for example, Simon Salomon and some of his students found that there were homogeneous Bach flat metrics in dimension 4 that they're actually on. I guess there are homogeneous metrics which are Bach flat but not conformally Einstein, not half conformally flat, and that might be a reasonable problem for somebody to try in dimension 6.
No, it's certainly interesting. Yeah. That's a good point. Well, I'm hoping that anyway that this sort of connection to higher Yang-Mills might help with such problems. Gives another tool.
Any other questions? Okay, then let's thank Rob again.
Thank you.